Hey guys, so today we're going to talk about deriving and calculating probability. So, theoretically, what is probability and how can we understand probability in real world? How does it manifest itself? So, to calculate your probability theoretically, there is a formula to do it. So probability of an outcome x meaning any outcome you want to insert, like getting ahead, let's say on a coin toss, rolling a tune, a die, etc. Probability of that outcome is going to be count of this outcome, the probability of which you're interested in, divided by all possible outcomes in the experiment. So remember that experiment is basically you doing a particular process and looking at the outcomes. So you're looking at all the possible outcomes and your outcome of interest. Let's do a quick example to illustrate. What is the probability of getting heads on a coin toss? Let's think about it. What's the outcome of interest on a coin toss? Well, it's pretty straightforward. It's in the question. It's getting heads, right? So getting heads. What are all the possible outcomes on a coin flip that are possible? This is a pretty simple one. There's two, right? We can get heads or we can get tails. So let's visualize it. Often it's really helpful in statistics and mathematics to visualize stuff. So all possible outcomes. Let's draw them out. We got heads and we got tails. So how many is that? That's going to be 2, right? 1, 2. And so all possible outcomes on a coin flip, we get a count of 2. And we see in the formula that this is going to be in the denominator, the bottom part of the fraction. So we got halfway there. What's going to be the numerator is going to be your outcome of interest, which is going to be heads. So how much of that do we have? We have 1. So our numerator is going to be 1. So 1 divided by 2 equals 0.5, which means that our probability of getting heads on a coin toss is going to be 50%. So this is a really basic understanding of how we're calculating probability theoretically. Now what's interesting is the following question. How do we validate theoretical probability in real life? So I just gave you a formula of how to calculate it. And it kind of makes sense, it's intuitive. But whenever we know what the probability of something is, let's say probability of getting heads is, that is 0.5, what does it really mean in real life? Well, we can kind of validate it by running experiments. So let's ask a question. It's always really important to question things and not just use formulas and understand what formulas are doing. Let's say a question: why is probability of heads on a coin flip 0.5? How does it manifest in real world? Well, we've already introduced the notion of experiment. So what we're going to do is perform an experiment many times. And we have a setup for this experiment. We have, as you can see, trials, outcomes, and the proportion. Proportion of heads is going to be the outcome of our interest, right? This is outcome of interest. And here we have just the outcome, whatever the outcome is. So let's make up some flips. So let's say I toss a coin once. So I tossed my coin. I got heads. So what does that mean? What's my proportion of heads? So my proportion of heads is 1 heads out of how many trials have I had? Only 1, right? So 1 divided by 1 is equal to 1. So my proportion is 1, so my probability is 1. So from doing just this one trial of this experiment, I can say that probability of getting heads is 100%. Wow. That doesn't really make sense, does it? That on a coin toss of a fair coin, which fair meaning like it can land either on heads or tails, you're 100% likely to get only one side. Doesn't really make sense. So that's why we don't stop just on one trial. We go to trial number 2. And trial number 2, we flip it. Oh, we get heads again. So now we have two outcomes of interest. The total count is going to be heads. The total count is going to be 2 because we have our heads here, our heads here. 1 plus 1 equals to 2. Divided by 2 trials equals to 1, equals to 100%. And we can later plot these on a graph. Okay, interesting. You know what? We're not going to stop at trial number 2. Now we're going to go a bit faster. Trial number 3. We get tails all of a sudden. Oh, interesting. So now we have 2 instances where we got heads out of 3 total instances. So this now is going to be 0.7 probability. So 70% of the time we can expect to get heads. Number 4, we get tails again. Remember, this is a theoretical experiment. This is, imagine me just flipping a coin, right? Anything can come up. Let's see, and we're looking at what's happening to the probability. So we got tails. That's 2 divided by 4, which is going to be 0.5. Oh, wow. We got pretty close to natural probability of getting heads, which is 0.5. Well, not close. We literally just got that number. Number 5, trial number 5, we flip the coin again. Now we get tails. So this is going to be, we got 2 heads out of 5 trials. So now it kind of dipped at 0.4, right? Interesting. So now it's 40%. Now we flip a coin again and we get heads. And now we have 3 out of 6, which is going to be 0.5, which is going to be 50%. So again, now we're, as you can see, like tending closer and closer to 50% or 0.5. Let's kind of plot it on this graph over here. So here's our, our y-axis is our probability. Our x-axis is the number of trials. On trial number 1, we got probability of 1. On trial number 2, we got probability of 1. And the probability meaning the proportion of heads in a given throughout in a particular trial. So on trial number 3, we get to 0.7. So we're plotting it here, right? Trial number 4, we got to 0.5. Trial number 5, we got to 0.4. Trial number 6, we got to 0.6. Do you see how this is kind of it's tending towards this value right here, towards 0.5. I know it's a made-up experiment with very few numbers, but the point is going to be illustrated. So, what have I been doing here? So if you perform a particular experiment, you do a trial over and over and over, like one trial after another, you're gonna invoke, I guess, this thing called the law of large numbers, which states that the proportion of certain outcomes will fluctuate at first, right? But later converges on natural probability of this outcome. So here is an illustration of this convergence. Basically, we have number of trials on the x-axis and proportion of heads of a coin flip on the y-axis. So as you can see, at first, maybe trial 1, trial 2, trial 3, trial 4, there's quite a lot of fluctuation, right? But as you get more and more trials, so this is going to be, let's say, trial 100, 200, etc. So we're kind of compressing the scale of the graph here. We're going to get convergence. And as you can see, it's converging to a particular value. And in this case, it's going to be 0.5. So we know that natural probability of getting heads is going to be 0.5. We can figure it out theoretically using the formula I mentioned, or we can just run an experiment over and over and over, flipping the coin, and measure the outcome, which is going to be heads. And as you can see, again, in an experimental fashion, the probability that we get of heads is going to be also about 0.5. So as you can see, the experimental proves the theoretical. It's going to be a similar value.